Hi, welcome to another session on biomaterials. Today, we're going to deal with mechanical properties of biomaterial. So, the mechanical property of a biomaterial basically requires the study of parameters such as the Young's modulus, the ductility, tensile strength, yield strength, compression strength, fatigue, and wear debris. But of whom? Well, it is for not only the biomaterial as well as the organ that the biomaterial is going to replace or the tissue that the biomaterial is going to replace. Human body has got various types of tissues. It's got the softest and squidgiest tissues of the brain to the extremely hard, stiff and rigid mineralized bone. So, depending on the organ that you're replacing, you need to choose your biomaterial accordingly. So, biomaterials that are used to replace rigid organs or rigid part of the human body should have Young's modulus that is close to the bone. Now, it is impossible for us to have a biomaterial for a unique biomaterial for each and every tissue of the human body. That's not possible. So we have to make some adjustments. That's why for anything that is hard and rigid as a bone, for example, the tooth should have biomechanical properties that is closely resembling that of the bone. So, because they assure uniform tensile distribution and avoid stress shielding after the implant placement. High values of yield and compression strength properties would avoid fracture, and if fracture is avoided, functional stability improves. Now, for these kind of material, it is okay to have a ductility that is around 8%. However, hardness and tenacity have got quite a lot of importance because hardness would reduce the wear incidence and tenacity would actually make fracture difficult for that particular material. So, if wear is reduced and fracture is also the probability of fracture is also reduced, then the life of the biomaterial or life of the implant is increased. So, these features, besides defining the processing ability of the biomaterial, are used to evaluate the success and the biocompatibility of the same. So, now, again, if you see, some biomaterials should have the ability to withstand cyclic load. Hip joints, for example, are subjected to a lot of different type of load. When you're seated, your hip joint do not bear as much load as when you're stood up. However, the load on the hip joint is not the same as when you're not the same when you are running when compared to when you're stood up. Even when you're running, each and every hip joint, like for example, during walking or during running, the leg that is planted firmly on the ground would bear the hip of the leg that is planted firmly on the ground would bear more weight when compared to the leg that is lifted up in order for you to run in your gait cycle. So, even during running, alternately your hip would bear weight and relax, and bear weight and relax, and so on. So, the joint that is the material that is used to replace the hip joint should be versatile enough to bear the cyclic load. It should not crack and it should not fracture for a really long period of time. Same is true with cardiac valves because heart is constantly pumping. The valves are constantly opening and closing, and it should be able to, the material that is used to make artificial cardiac valves should be able to bear this cyclic load. Now, fatigue is another factor that can occur in a biomaterial. Human body, when it is subjected to a lot of stress, gets tired. So similarly, biomaterial should not lose its originality or should not, crack when it is subjected to numerous cyclic load. So that shouldn't occur. So, biomaterials that should bear cyclic loads, like for example the cardiac valves. So, with this is this it bears cyclic efforts without cracking propagation. and they are usually made of either metals, polyurethane, or polyesters. Now, wear occurs when two surfaces are in constant contact with each other. So when the two surfaces rub against each other. So this can occur in a joint processes. So joint processes, like for example the hip processes, when if there is no material padding in between the hip processes and the iliac fossa, then the processes would directly rub against the bone. So bones are highly vascular, highly innervated. So that's why rubbing against the bone is going to be a very painful experience. So we put a padding in between the bone and the hip implant. So this pad now instead of rubbing against the bone, the implant would rub against this padding. Now, over a period of time, this material is gonna wear off. However, our job as a biomaterial expert or an implant designer should be to choose a material who that is not gonna wear off as quickly. For example, you just had one person had an implant today, and 6 months later, if this material is worn off, then that is not acceptable. So our job is to delay the wear as much as we can. Also, physiological medium or the environment the material comes in contact with also aggravates the wear phenomena. Now, if you take the example of an intervertebral disc, now these are various types of examples that I'm taking to make you understand how versatile the selection of biomaterial is based on the application. So intervertebral discs are subjected to a lot of compression force, and when they are compressed, they radially transmit the energy across the surfaces. So that is the property of an intervertebral disc. And when we are using a biomaterial to replace the intervertebral disc, we need to make sure that this property is totally replicated or replicated as closely as possible. Now, this compression force also varies from activity. So when you are like like when you are weightlifting, then it is estimated to go up to 2,500 newtons. So when you are like doing routine activities such as climbing the steps or jogging, then the pressure on the intervertebral disc varies. It's not more than 1 megapascal. So your material should be such that it should withstand this force and this approximately this pressure. That's all we have for today's session. I hope you had a fruitful session and I shall see you in the next one. Thank you very much.